So, let us look at the magnetic resonance phenomena in quantum mechanics, and in particular we are going to talk about nuclear magnetic resonance. However, we can sort of the same formalism would go through for other resonance phenomena, which we will just briefly mention. As an introduction to NMR or nuclear magnetic resonance, can be said that if a sample is placed in a magnetic field and then it is subjected to a radio frequency radiation. So, at appropriate values of the frequencies, the nuclei in the sample can absorb radiation. Now, of course, one knows that nuclei do not exist alone or individually in a sample. They are always surrounded by electrons, as we know of an atomic structure, and so basically that will give information about the environment of the nuclei. But here we are particularly talking about the response of the nuclei and not of the electrons to that external radio frequency radiation that is mentioned here. So, the frequency of radiation necessary for absorption of energy or the radiation, that depends on three factors. That is the type of the nucleus. So, whether you have hydrogen or you have carbon. So, it will the absorption frequency or the emission frequency would be different, and then the chemical environment of the nucleus, and this is what we were trying to talk about, that the environment is important, and if a particular nucleus is chemically different than another nucleus, so this frequency will change as well in that case. And the spatial location of the sample, especially if you have an inhomogeneous magnetic field, and this is the principle that is used in MRI. So, these are the three factors that the frequency of radiation that will depend on. So, going ahead with the discussion, nuclei have positive charges. Usually the nuclei behave as if they are spinning about a certain axis, and if there is a magnetic field, external magnetic field precess around that in a conical fashion. Since they have charges and they are spinning or rather moving, then the classical electromagnetics says that electromagnetic theory says that anything that is charged and moving should have a magnetic moment, and hence produces a magnetic field. This tiny magnet or this magnetic field that is produced by the nucleus is called as the nuclear spin. If we put this tiny magnet in presence of a large magnetic spin, then the nuclear spin will assume two orientations, and we are particularly talking about spin half for the nucleus. So, that is nuclear spin equal to half. So, there are possibilities that this nuclear spins will align in the direction of the field, which is parallel to the field, or they could align anti-parallel to the field, and one of course has lower energy than the other. We will see that in details. So, for a large number of nuclei, the spin is actually half. The most common examples are we have given two already, that is carbon and hydrogen. In addition to that, there are nitrogen, and then there are fluorine and phosphorus, and for these nuclei, this two-state description is particularly relevant. So, what is this NMR and how do we understand it? And the simplest form, we also know about infrared spectroscopy, which is the simplest form or rather example of transitions being induced by the oscillating electric field of light or photons. So, NMR likewise is the simplest example of transitions induced by the oscillating magnetic field, and we have already talked about the oscillating the frequencies in the radio frequency regime. But because the strength of the matter magnetic field interactions, so this is are typically quite low, in fact 2 orders of magnitude lower than the corresponding electric field counterpart, NMR is actually a much more delicate probe of structure and properties of materials. And so, magnetic resonance phenomena denote absorption or emission of electromagnetic radiation by the atomic nuclei or even the electrons in presence of an external magnetic field. So, the resonance phenomena, the other resonance phenomena that we are aware of includes ESR, the electron spin resonance, and of course, the one that is under focus is the nuclear magnetic resonance. So, in particular, we shall talk about NMR. However, the formalism is for resonance is valid for ESR as well. Now, NMR was discovered by E. Parcel and F. Bloch in 1946, and it has important applications in determination of the molecular structure, the dynamical measurements in the liquid and the solid state, and the MRI that we are familiar with, which is used for as a very important diagnostic tool for several kinds of diseases. So, let us try to understand the mechanism of NMR. So, consider nuclear spins interact with an effective magnetic field comprising of 2 parts. So, one is or rather 3, let us see, an external magnetic field, which is homogeneous and in a particular direction, and of course, the preferred direction is most of the times is say z direction. Number 2, that is an internal magnetic field due to the presence of other nuclear spins. Okay. And a third, and importantly, a radio frequency RF magnetic field that can cause transitions between states of different quantum numbers, or rather spin quantum numbers or magnetic quantum numbers. All right. So, let us see that how these 3 factors affect, or rather how we can write down a minimal Hamiltonian for all these 3 kinds of interaction. So, we all know that the Zeeman Hamiltonian written for a single spin in presence of what we said as a constant h 0 in the z direction and 2 and R f in the x direction. So, this is like h 1 cosine omega t x cap, where omega is the frequency of this RF field, and then the Hamiltonian H is written as minus mu dot H of t. Remember, we are writing the curly H for the Hamiltonian and a straight H as we in block letters or bold letters for the magnetic field. So, this is equal to, so H of t equal to H 0 z plus H 1 cosine omega t x cap. Now, it is important to sort of also know that, which not very relevant for us in terms of computation, but this is replaced by a circularly polarized field of the form, say, H 1 cos omega t x cap plus a sin omega t y cap for diagnostics such as MRI, etc. Okay. But here for our case, it is simply in the x direction with a cosine variation. Now, we have another term which we had forgotten, or rather not taken into account so far. In fact, this one, if you see, it is number 3, and let us talk about the number 2, which is interaction between the spins. Now, this is one can assume a spin dipolar interaction between the spins having a form and it is I am disregarding the dimensions, that is putting the interaction dimensions. Simply this is like this, which is S I dot S j R I j square and divided by R I j to the power 5. So, this is a generic dipole-dipole interaction that is familiar in the context of classical electromagnetism, and that can be taken as the interaction between the spins. However, it is often what is done is that this term is neglected, and this term is in some sense included in the H 0. So, let us write down the simplest approach. Is to add a term to the effective magnetic field due to this interaction. And the reason for underplaying the contribution of the spin-spin interaction is that in many systems such as particularly in liquids, you have we are talking about spin liquids, your Rij's change so fast. Rij's are the distance between the spin at site I, Si and Sj, the spin at site j. These change so fast that the averaging over configurations would yield a 0. However, it is not always true. In fact, in presence of an RF field which actually measures the time interval over which this change takes place, that is this Rij's change, because in a spin liquid there will be no fixed Rij's at all instants of time. So, if one takes an average, then it gives a very small contribution. However, it is still a contribution which can be neglected, or as it is written here, it could be added to the effective magnetic field. So, this interaction can be actually included indirectly into the changing the external magnetic field, the constant magnetic field, by a small value. So, what happens is that after excitation by RF pulse, the spins in turn produce RF signal that can be measured subsequently. One can Fourier transform that signal to obtain the frequency spectrum of the sample. So, importantly, the peaks in the frequency spectrum and their widths carry signatures of the spin states of the let us write it as a chemically different nuclei and their environment. So, these are the signatures that carries the NMR spectroscopy signatures for all the information that one wants to get about the structure, the magnetic structure of a system by NMR spectroscopy.